Welcome to this Chapter 16 video where I discuss memory segmentation. My name is John Jolly. Let's continue. So, with the memory management we've talked about so far, we can call this contiguous memory. We call it contiguous memory because the memory address for a process starts at 0 and goes to the end of whatever the address space is. In this example here, we have a 16K address space. So it starts at 0 and goes to 16K. This entire address space must be one long unit of 16 kilobytes. That's how it's going to be allocated in physical memory. The reason for this is because we have the one base and bound set of registers. Those registers, the base, it only has one value, starts at 0. We don't have separate values for different spaces in memory. And the bound covers 16 kilobytes. So when you think about the physical memory, all of this has to be in one long group of 16 kilobytes. Now consider our contiguous memory here. We have our code segment, which has our program and is the data that was loaded from the program file. We have our dynamic memory called the heap, which grows down, and we have this dynamic memory called the stack, which grows up. In this particular case, the heap is 2 kilobytes in size. It goes from starts at 2 kilobyte, ends at 4 kilobyte. It is a total of 2 kilobytes. And the same thing is true with the stack. The stack began at 16 kilobytes, is currently at 14 kilobytes. So in total, I have 2 kilobytes here. So with the heap and stack combined, we have 4 kilobytes. But we have a total of 14 kilobytes from the end of program code to the bottom for dynamic memory. This means this free space is a full 10 kilobytes of memory that cannot be used by any other processes. Why can't it be used by another process? Simply because this has been allocated for our process. And you can't assign a base address in the middle of our process's address space. That would be a bad thing to do. It would cause one process to potentially overwrite another process. So 10 kilobytes here that cannot be used. This is actually an inefficient way to allocate your memory. What if we never use more than the 4 kilobytes of dynamic space here? Well, this 10 kilobytes continues to go unused for the duration of the process. We call this internal fragmentation. This is a fragment of free memory here that cannot be used by any other processes. So it remains free until, of course, this process decides to use more memory. It remains free and unusable, even though it could be used if we did things a different way. There's also this added problem of what happens if we collide here? What happens if these two dynamic memories collide? Is there a way to space this out to create more space? Right now, 10 kilobytes is a certain amount of free space, but maybe we want to have a larger address space. Consider if we had not 16 kilobytes, but 16 megabytes of address space. This free space could be 16 megabytes in size. Or consider process address spaces today, where the process address space is actually 4 gigabytes in size. 4 gigabytes is a very large address space, and that 4 gigabytes would only have a little bit of stack and a little bit of heap, which means we would literally have gigabytes of physical memory unusable because this process had it all allocated. So as we increased address space sizes, this became much more untenable to work with. So what are we going to do? We're going to create what is called segmented memory. We'll take the different segments of our particular program address space, like the code segment. the heap segment and the stack segment and give them their own base and bound register. So instead of one base and bound register per process, now we can use 3 base and bound registers. We'll use one base and bound for the code. We'll set that value to 32 kilobytes. We'll have a second base and bound for the heap. We'll put that at 34 kilobytes. And then we'll have a third base and bound for the stack. Now the stack is a little bit different because the stack, unlike the heap which grows down, the stack grows up. We'll talk more about how we're going to work with that, but we'll set a different base and bound for the stack segment. Now, if the heap needs to grow, it can grow into this unused space. And the stack can also grow into its unused space. So if I need to allocate more memory for the stack, then I can use this space without having to worry about whether I'm going to conflict with the heap or not. Now, how do we actually perform this operation? How do we decide which base and bound register we're going to use? Well, considering we have 3 segments here, we can actually address the 3 segments using just 2 bits. With just 2 bits, we can actually address a maximum of 4 segments. We're only needing 3, but 2 bits are still necessary. So let's just simply take the high bits of our virtual address to determine which segment we're using. Here's an example that we have of a virtual address. In this virtual address, we take the 2 bits and we identify the segment based off of those 2 bits. We can give each value of these 2 bits a particular segment type. So like if the bits are 0, 0, this will be the code segment. If the bits are 0, 1, this will be the heap. And if the bits are 1, 1, then this will be the stack. And you can see here in this particular address, we have a virtual address that is 1, 0, 6, 8. 1 tells us that this is the heap segment. And so what would happen is the CPU would find the base value here and the bound, or the size in this particular case, and it would first check to see, is the 6.8 within the 3 kilobytes? It is. So success. And then it would take the 6.8 and it would add it to the base register. So we would end up with an address of 8868 for the physical address. If this were the stack would be treated a little bit differently. We've added an extra piece of information. So we have our base, our size, which is our bound. Now we have a grow positive field. And you'll notice our code and our heap both have grow positive, meaning that our base is at the top of the memory range. But for the stack, we have a 0, which means it does not grow positive. It is a negative growing segment, which means our base is at the bottom of our range, and that addresses need to be subtracted from this. So for example, if we had a stack address of 3FC2, that 3 tells us 1, 1 is our segment or the stack segment. And so this FC is used to go backwards from our stack base address of 28K or 7,000 to go to 6FC2 into the stack. So this bit tells us instead of adding, we actually go backwards or subtract. In this way, we have a way of addressing a particular piece of memory virtually that allows us to use different segments to work with. There is a second way that segments can work. We call this explicit segment addressing. But there's also something called implicit, where there isn't a segment address at the end. It's all one big offset. And the way the segment is decided is based on how the address was created. There are some instructions that create an address from the program counter. Program counters would go to the code segment. There are some instructions that work with the stack pointer. Move the stack pointer into another register. Those addresses would go to the stack segment. And everything else that doesn't either work with the code segment or the stack segment would end up as a heap segment address. That way we can not have to worry about using our virtual address space to identify a segment, use the actual instruction to do it. We don't see this dynamic segment identification very often, but there have been systems that have used it. So what are some of the benefits of segmented memory? Well, we can use a larger virtual address space. So instead of just simply using the 16K we have, we can use much larger. Now imagine a 4 gigabyte virtual address space with segmented memory, when all that process was using was 60 kilobytes. We have nearly 4 gigabytes of unused internal fragmentation. Yet with this address scheme, with segmented addressing, we can have our 4 gigabyte virtual address space, yet the process will only use 60 kilobytes of physical memory, thus eliminating internal fragmentation. One of the nice benefits of segmented memory, if we need to move any one of the segments or multiple segments, we can move just that segment and change the base address. So maybe we need to move the code segment somewhere. We can just simply take this code segment, copy it to a new physical address, and then change the base for the process, and everything works fine. We also have the ability to set the size within each segment, meaning that if we get a virtual address that doesn't fit within the size, we can generate what is called a segmentation fault. In contiguous memory, a process could access anywhere in its address space, even if that address space wasn't officially allocated. But with segmentation, we can actually say you addressed a piece of memory that was outside of what was currently allocated. One nice thing about segmented memory is we can now share segments. Consider for a moment we have two processes, and both processes have the same program file. Well, the program file isn't going to change. It's instructions, and we don't want the instructions to just simply modify themselves. So what we do is we allow that particular those processes to use the exact same code segment base address and size address. Now, to prevent one process from actually changing the code of another process, we protect that memory with some extra information. So we've added a fourth field to our base and bound. We have the grow positive field, and now we have a protection field. This protection tells what you can do with that memory, and each instruction is checked to see if it matches this particular protection. So if an instruction tries to write to a virtual address that's in the code segment, a segmentation fault would happen because you cannot write. You can only read or execute. This also provides protection with the heap and stack. If a process tries to execute an instruction in the heap, because the heap doesn't have the execution protection, that would cause a segmentation fault. This really helps whenever you want to ensure that a process isn't able to just simply create a code on its own and run it, which is a major problem whenever it comes to malware. Malware would very frequently create code in the heap and then execute it. And this prevents that from happening. Some of the problems we have with segmented memory. Consider for a moment a memory address space like this, where we have 3 allocated segments. Those 3 allocated segments each take 8 kilobytes. The gap between each of these is also 8 kilobytes. Clearly, we are not, these visuals here are not to scale. But each of these not in use are also 8 kilobytes in size. Well, what happens if I need to allocate 16 kilobytes of segment space? Let's say I wish this allocated space here is the heap, and I want to grow the heap down by 8 kilobytes. Well, clearly I can't use any of these to copy this to another 16 kilobyte area. To do this, what I need to do is move all of these allocated spaces together. That way I'm eliminating all these empty gaps between. So let's say I put the code, the stack, and the heap into one long allocated area. They're still separate segments, but they are compacted. Now I have 24 kilobytes I can work with, and I can allocate 16 kilobytes if necessary. One other problem with this is because we're using a specific offset value in our virtual address to address into a segment, that segment cannot grow beyond its offset value. If right now our particular segments are 4K in size, if our heap grows to be greater than 4K, we can't create a new heap segment. We can't create a second heap segment and attach them. It just simply we simply can't have those segments in that way. So segmented memory does have problems, and we will resolve those. So maybe what we need to do is come up with a way to allocate multiple segments. And we'll discuss how we can do that later. This brings me to the end of chapter 16, where I discuss memory segmentation.